Welcome back to Electrochemical Engineering. Today I'm going to give an introduction to battery fundamentals. On the left is the first voltaic pile developed by Alessandro Volta in Italy in the year 1800. On the right is modern batteries. Here they're showing different form factors. AAA battery, a AA battery, an 18650 cell. Notice 18 and 65 are the dimensions of the cell. Notice that the 18 and the 65 are the dimensions of the cell, the diameter and the length of the cell. 2170 cells are a larger version, which allows you to save weight of packaging materials and more efficiently use the active material and obtain higher energy density with the same chemistries. Some companies are really pushing the limits, developing much larger cells for use in electric vehicles, where weight really matters. 18650 cells are what you typically find in your laptop. Let's look at the invention of the battery, Alessandro Volta's voltaic pile in the year 1800. Volta built the voltaic pile to challenge Luigi Galvani's claim, where he claimed to have demonstrated that animals produce electricity. It turns out that Galvani's results came from using two dissimilar metals connected by a frog leg, which is an ionic conductor. Here's a picture from Galvani's original work. The frog leg would move in response to the electrical current passed through it ionically from the dissimilar metal contacts. Volta's cell looks like this. You have a copper plate and a zinc plate. The zinc is more reactive than the copper. Copper is a more noble metal. So this forms a galvanic cell. They're placed back to back, and there's a separator in between them that is typically brine-soaked paper. This brine-soaked paper acts as ionic conductor between the two metals that have dissimilar electrochemical potential of the electron. This leads to a voltage. Every cell has a voltage, and those voltages add. So the total voltage of this voltaic pile can be very large. Can you estimate the approximate voltage output of the voltaic piles shown below? These large voltages can be used to electrolyze water, to make hydrogen and oxygen, and in fact, were the first way those elements were isolated. Humphrey Davies and others used these voltaic piles to isolate many elements from compounds and actually lead to the discovery of those elements and the start of modern chemistry. Let's talk about battery basics. A battery cell has several components. It has a negative electrode. That's the material which is more reducing, and that's the zinc bar in this. The positive electrode in this case is a copper bar. The positive electrode is typically made of the more noble metal. The electrolyte here is the solution into which the metals are placed. Here, a salt bridge is used to connect the negative electrode to the positive electrode. You might think about why such a salt bridge, as shown here, might not be a good choice in commercial applications. Note that in all batteries, the electrodes are isolated from one another by a physical separator. Here it's two beakers, so the electrodes can't touch. The electrons cannot transfer directly from zinc to copper. They need to go through the solution and pass as an ionic current by driving Faradaic reactions, redox, at the surface of the electrode. Usually in commercial batteries, of course, you don't use two beakers, use a thin separator. The electrode undergoing oxidation is the anode, and the one undergoing reduction is the cathode. So in this case, the cathode is the copper as this cell is discharged, and the anode is the zinc. However, when the battery is charged, the process is reversed. The electrode that is the anode upon discharge, i.e. the zinc, is the negative electrode, and the one that is the cathode during discharge is the positive electrode. Consider a 9-volt battery, shown here. I've labeled the positive and negative electrodes. Those never change from being positive and negative. When the battery is being discharged, the negative side is connected to the anode. This is where the electrons come from, and hence its negative potential when the battery is being discharged. However, when the battery is being charged, the reactions are driven the other way, so you need to swap which one is the anode and which one is the cathode. Let's now talk about a more complex modern battery, the lithium-ion battery. A lithium-ion battery also has an anode and a cathode. The anode is typically graphite. That graphite can intercalate lithium, here shown as these spheres. These are zero-valent lithium, so lithium 0 has a potential near metallic lithium. So the electrons in that lithium are very reactive. There's also lithium cations in the electrolyte that are able to move in either direction in response to the cell being charged or discharged. These lithium cations are, of course, coordinated by solvent molecules that stabilize them. When the battery is discharged, lithium is oxidized here, going from lithium 0 to lithium plus, releasing an electron to the external circuit. That electron in the external circuit can do work and return to the cathode, where you reduce transition metals in a lithium metal oxide layered structure. The metals are typically cobalt, nickel, or iron. The active material, in this case metal oxides on the positive electrode, are typically fabricated on what's called a current collector. This current collector is aluminum because it's stable at the potentials that this electrode works at, and it's lightweight. At the anode, the negative electrode, copper is used as a current collector because it doesn't get lithiated at the potentials it operates at. We'll talk more about that soon. Modern lithium-ion batteries, the details of their operation is incredibly complicated and has been the subject of intense study for the last several decades. We'll talk about many of these concepts throughout the next several lectures. Over here, on the left side, some of the advances that have enabled high-performance anodes are discussed. We'll talk about how dendrite issues had to be solved, how graphite electrodes had to be protected through the formation of a SEI layer, a solid electrolyte interface layer that allows for stable cycling. We'll talk about the role of graphite and staging in the intercalation. There's also been substantial work in the electrolyte development. The electrolytes are typically organic soluble electrolytes, and the solvents are things like ethylene carbonate and propylene carbonate. They're ethers that solubilize lithium well, but are stable relatively under the high and low applied potentials in a modern battery. The cathode has also been intensely studied, but is an area where there's still a lot of opportunity for new materials development, and in fact, many companies are trying to do this. There are several different types of cathodes that we'll talk about, and the redox potential of the cathode largely determines how much voltage the whole battery is able to offer. Different metal cations have redox levels at different states, and that can be used to tune the overall voltage of the battery. Let's go to some simpler batteries first. Here's a cross-section of a commercial silver-zinc coin or button cell. This is something you might buy at the store, for example, to power your watch. In this case, you have a separator that's a porous film or matrix. You can see the separator here is this yellow band. You have a negative electrode and a positive electrode. The active material is shown here, and that material must conduct both ions through the separator and electrons back and forth between the current collector and the bulk of the active material. So this is where the porous electrode theory that we developed in the previous lecture is really important to understand the limitations and the opportunities in these batteries. Notice here there's a gasket separating the positive electrode current collector from the negative electrode current. The typical silver zinc cell operates by this overall chemical reaction. Zinc, which is a highly reducing chemically reactive metal, reacts with silver oxide to form zinc oxide, a very stable oxide, and silver metal, a stable noble metal. This is what's called a primary battery. Primary batteries are not rechargeable. Why do you think this battery is not a rechargeable battery? We'll talk about some of these concepts later as we discuss secondary or rechargeable batteries. We can use the Gibbs free energies of formation and the methods from Bard and Faulkner to calculate the standard potential for the cell. Notice that the standard potential here, U theta, is equivalent to E naught cell in Bard and Faulkner. U theta equals negative delta G of the reaction, the overall reaction, divided by NF. We can input parameters and get that the voltage for this battery is about 1.6 volts. You should, of course, be able to take any battery chemistry and easily calculate its standard voltage. Here are the two half reactions for the silver zinc cell during discharge. The cathode reaction is silver oxide plus water plus 2 electrons goes to silver and 2 hydroxides. And here's its standard potential, standard reduction potential that you can look up in a table. The anode is zinc getting oxidized to release 2 electrons in water and make zinc oxide. Here's this standard reduction potential. Notice that even though this reaction is written as an oxidation, this is the standard reduction potential. E cathode minus E anode gives the overall cell potential. This overall cell potential is positive, indicating it's a spontaneous reaction. Because silver has the higher potential, it is referred to as the positive electron. Because zinc has the more negative potential, it's referred to as the negative electron. It's the source of the electrons when the cell is discharging. Note that hydroxide is involved in the reaction in both electrodes. We'll have to use hydroxide in our electrolyte. So these cells typically work in alkaline electrolytes. Water is made at the zinc electrode and is consumed at the silver electrode. So the net amount of water and hydroxide remains constant as the cell charges or discharges. Let's discuss a little bit of battery terminology. We already mentioned the difference between primary and secondary. Primary batteries are single use, whereas secondary batteries are rechargeable. I mentioned why primary batteries are only single use. It's typically because the reactions can't be easily reversed, usually due to some sort of phase change or phase separation or loss of electrical conductivity in a product. But primary batteries usually have higher specific energy, and there's more types of materials that can be used in primary batteries than rechargeable batteries. Another concept is the reserve battery. In this case, some component of the cell, for example, the electrolyte, is kept separate or inactive. This is important because it reduces the self-discharge rate of the battery, which are due to side reactions, and increases the shelf life. For example, if the electrolyte is a solid and the cell activates when it's heated to melt the electrolyte, when the electrolyte is a solid, it doesn't allow self-discharge. But when you heat the electrolyte, the battery becomes active and you can use it in an emergency. I'd also like to highlight the difference in terminology between cell and battery. A cell is the basic electrochemical device that stores the energy, i.e., the positive and negative electrode, the electrolyte between it, and the separator. Two or more cells connected together form a battery. It is common to refer to a single cell as a battery, even though there is only one cell. It's better to call a single cell a cell and a battery multiple cells in series. Now let's classify different types of battery chemical reactions. During chemical reactions in a battery, new phases form and grow, while others shrink and disappear. These can be classified as either formation or displacement reaction. Here's an example of a formation reaction. A and B form a new compound AB. That may or may not be a reversible reaction. That is, this can be used in a primary or secondary battery depending on the specific materials chemistry. Another type of reaction is the displacement reaction. Some element A reacts with a compound to displace element B and form a new compound. Let's do some examples. Here's a formation reaction, is the lithium sulfur dioxide primary cell. This battery is still used commercially. You take lithium metal, react with SO2 to make lithium sulfate. This is a spontaneous reaction and releases substantial free energy. The zinc-silver battery we discussed before is an example of a displacement reaction. You can see here that it is zinc displacing silver in the overall cell reaction to form a more stable zinc oxide phase and noble metal. This sort of classification is not sufficient to understand the mechanisms of battery operation, so we'll take a more detailed look. Consider the following. This is called the dissolution precipitation mechanism. M, for example, is a metal that's used as a negative electrode of the cell. In this reaction, the metal dissolves to form a metal cation and release electrons that can go and do work in the external circuit. This is the dissolution step. The next step might be the reaction of that metal with some anion in the electrolyte to form a new compound, MXZ, where Z represents the stoichiometry of this precipitation reaction. Now, the amount of MXZ precipitated depends on the solubility in the electrolyte of the compound formed. We'll consider three conditions for that solubility. One, a highly insoluble salt, a highly soluble salt, and an intermediately or sparingly soluble. Let's take the example of an insoluble salt. This is the positive electrode for a lithium thionyl chloride battery. So the negative electrode is the lithium metal. The positive electrode is thionyl chloride, this compound here, SOCl2. SOCO2 can be easily reduced with the electrons released from the lithium that come from through the external circuit to chloride, sulfur, and SO2. Those products, in this case Cl minus, combine with lithium plus in the electrolyte to form lithium chloride. Lithium chloride is highly insoluble, it's a highly ionic compound. It's highly insoluble in the electrolytes used. So the chloride is created as SlCl2 is reduced. It runs into lithium plus almost immediately, as lithium plus is in high concentration in the electrolyte, and it precipitates at the site of the SoCl2 reduction. There's essentially no Cl minus in solution. Without Cl minus in solution, the reaction is irreversible because lithium chloride is a salt and it's electronically highly insulating. This battery is thus a primary battery. Now let's consider a case where the salt is highly soluble. This would be the zinc electrode in an alkaline electrode. Zinc metal can release electrons easily. It's a strong reducing agent, reacting with hydroxide to form this zincate 2- anion. This anion can react to form zinc oxide, hydroxide, and H2O via precipitation. Now, imagine the solubility is so high that no precipitation of the zincate ion occurs at all. Then the zincate ion would be able to diffuse or transport throughout the solution. Now, it's no longer concentrated where the reaction takes place. This seems good, but the issue is that upon recharging, the current distribution on the electrode becomes non-uniform. That is, you can drive these reactions backwards and replate zinc, but that zinc is plated in a non-uniform way. Sites where the deposition and precipitation are higher will grow in size. This leads to changes in the electrode shape, and it can even lead to the formation of dendrites. So zinc electrodes are typically only moderately reversible, though there's been a lot of science advances and even several companies that we have interns placed at working to advance this exciting technology. Zinc is exciting because it can store 2 electrons per cation, and it's a cheap metal that is abundant in the Earth's crust. Let's talk a little bit more about dendrites. Dendrites are rigid, tree-like structures that form from metal plating. Usually it's lithium, but also zinc, as we just saw, plating onto an electrode during battery cycling. So in a classic case, here's a lithium anode. This is another thing that people are working hard to make work, because if you could store lithium as a pure solid, you could increase the energy density of a battery. But when you dissolve and replate that lithium, it starts to create these self-amplifying structures that move through the cell and can even short circuit your battery, moving through the separator. The electrochemical potential can create a very large internal pressure that allows these metal spikes to push through even fairly hard materials. If those whiskers penetrate the separator and reach the other electrode, it short circuits the cell. All the electrons from here move straight over to the cathode, releasing all that stored free energy inside of the cell instead of in the external circuit. That leads to a lot of heating, and the flammable electrolytes used in lithium batteries can actually catch fire. Dendrites form because growth on an existing protrusion is more favorable due to better mass transport than growth on the surface. Here's an example. If I have uniform lithium, I start to plate it and nuclei form because of the cohesive energy of lithium. Those nuclei are further away from the electrode surface than the areas that have not yet been plated with lithium. Thus, they are more likely to have another lithium cation collide with those slightly higher areas, leading to preferential growth there. You can see that over multiple cycling, these dendrites can get larger and larger and larger as they become further removed from the surface. During battery cycling, a dendrite whisker can even break off, sequestering that metal from recharge cycles and decreasing the rechargeability. There's a number of interesting studies from the recent literature looking at how to suppress dendrites or how to recondition batteries to prevent dendrites from causing damage to the cell. Here's an example from science where they used a lithium metal anode. They can form dendrites under normal charge-discharge cycles. But if they use high energy pulses, they can burn out those dendrites, smooth and self-heal the anode. Here's a second example from the very recent literature. In this case, the authors from Stanford University, Yi Sui and his team, looked at isolated lithium metal dendrites that had broken off of the negative electrode. These isolated lithium can be polarized in a strong electric field. That polarization can lead to the actual dissolution of lithium from the isolated lithium dendrite. When you do that, you can actually dissolve these dendrites that have broken off and replate them on the lithium anode and reuse that lithium. So this is another example of a cell conditioning cycle that can be used to reclaim lost lithium to deal with the dendrite issue and potentially to use a pure lithium anode. Let's go back to different type of chemical reactions. Let's talk about a situation where you have an intermediate or sparingly soluble salt. One example of this is the negative electrode of a lead acid battery. At the negative electrode, you have lead releasing electrons, forming lead 2 plus. That lead 2 plus reacts with sulfate in the sulfuric acid electrolyte to form lead sulfate solid precipitate. Lead sulfate is non-conducting and only sparingly soluble. So as the battery cycles, i.e. charges and discharges, a lead acid battery is typical a secondary battery, the lead sulfate product is repeatedly formed and dissolved at roughly the same location since the solubility is low. The solubility is large enough to allow for the reverse reaction, but it's low enough to prevent the formation of substantial dendrites. This battery is therefore a secondary type battery, and this battery is used commonly in automobiles for the electric starter. Let's now talk about insertion electrodes. Insertion electrodes are how lithium is stored in a modern lithium-ion battery. One of the first insertion electrodes studied was titanium disulfide. Titanium disulfide is a layered structure held together by weak van der Waals forces. Here is the titanium cation in this gray sphere, and the sulfur coordinates that cation to make two-dimensional sheets of covalently bonded material. These two-dimensional sheets are only weakly held together by van der Waals forces. That is, the weak non-covalent bonds between the two sulfur. When lithium is inserted into this cell, it reacts with the titanium sulfide to form a lithium titanium sulfide. The electrons are reducing the titanium, formally taking them from +4 to +3, and inserting a lithium cation in between the sheets. This space is known as the gallery space. When x equals 0 in this formula, TiS2 is said to be delithiated, and the electrode is charged. It's ready to accept lithium from the negative electrode, which, for example, is lithiated graphite. When x equals 1, titanium disulfide is lithiated, you have this compound, and the electrode is discharged. You might think about what the oxidation state of lithium is across all these compounds. Finally, I want to talk about graphite. Graphite is used at the negative electrode. There's an interesting phenomena that occurs when you insert lithium into a lithium-ion battery. This is called staging. When you add lithium, it begins to insert between two graphene layers, as shown here. Lithium will preferentially insert into that layer until no more lithium is able to insert. If you think about it, this makes sense. Once you start peeling apart the layers of graphene, it's like wedging apart the pages of a book, it's easier to get the next lithiums in. Now remember, the oxidation state of these lithiums, these are nominally lithium 0 because it's used at the negative electrode of the cell. All that space is filled with lithium before you wedge apart another set of sheets of graphene. These lithium sheets tend to be ordered so they're a fixed distance apart. That's because there's a strain field from pushing those lithiums in. So the charging looks like going from stage 4 to stage 3 to stage 2 and to stage 1. The most lithium you can fit is having a layer of lithium interleaved with a single layer of carbon. And this occurs at the most negative of potentials when you're charging a lithium ion. So that's all I want to discuss today, and I look forward to seeing you all in class so we can work through some examples from this material.